Welcome to the fifth session of Physics Talk 2021. I am Mohammad Abdusami Akondo, a junior student in Physics discipline, Khulna University. It is my great pleasure to introduce our speaker, Mohammad Salahuddin Mina. He is currently a PhD fellow in Incheon National University in the Republic of Korea. He is also an assistant professor in physics discipline, Khulna University. Without further delay, I would like to request our speaker to start his talk.
Okay, thank you, Abdusami Akond, for your kind introduction. So, I am MD Salahuddin Mina, and a faculty of physics discipline, Khulna University, Bangladesh, and currently I am doing my post-graduation degree in South Korea. So today I am going to talk about some my research field. So actually, I designed my talk on the chalcopyrite based thin film solar cell, and there is several part of fabrication of solar cell. So one of the part I will just cover the efficiency improvement by solution based non-vacuum chemical spray pyrolysis method. So this is one of the very easy method and cost effective method around the world. So in our lab we are just doing this method for fabrication of the solar cell. Uh, Here there are various types of solar cell around the world. So one of them is some chalcopyrite or some ceramic based material, so thin film solar cell, and there are several methods to improve the efficiency. How we can improve the device efficiency, and actually our main ultimate of this research, how we can make the perfect solar cell with cost effective and not it requires not so much uh, productive cost. So that's our main concern, how to improve the device efficiency and how the method is applicable in all condition. So mainly in our lab we are fabricating the device solar cell, some non-vacuum chemical spray pyrolysis method. Actually many methods are implemented for fabrication of solar cell, but most of them are some it's requires some high vacuum process. So you guys know high vacuum contains very costly, and it's not convenient for large scale fabrication. But in our lab we usually fabricate some non-vacuum, that is some ambient air condition, and it's also some solution based chemical spray pyrolysis method. So I am very much grateful to of my collaborator of this work, my professor and others lab mate who contributed to published and complete this research work. Actually today I am just focusing on of my papers. So these authors are the contributor of these papers. So today my presentation outline covers some basic concept of semiconductor materials and solar cells, and then for the second part in our lab the some fabrication approach and characterization approach that we used for analyze and fabrication of our solar cell, and third is some experimental research outcome, and finally I will make conclusion of my research outcome. So actually first if we consider some solar cell, actually solar cell is nothing just for some semiconductor materials. And in we know for the semiconductor materials there are two types of p type and n type semiconductor materials. And for the solid state material we know there are three types of materials. Some is insulator, semiconductor and conductor. In semiconductor there are two types, p type semiconductor and n type semiconductor. So here I will just show many types of semiconductor materials regarding their band gap. So usually for the fabrication of solar cell, some of these semiconductor materials are usually used. And this is also some concept of semiconductor materials that were when we make the device fabrication, that we are concerned about some property about the conductivity and resistivity. And also in the periodic table we know there are several elements, so all elements cannot be used for fabrication of solar cell. So some of the elements their inherent properties and chemical composition that will be very much effective for the fabrication of solar cell in the solution based method. And if we consider some energy band diagram, so this is for semiconductor materials, this is some conductor, and this is some this is some insulator, conductor, and semiconductor material. So for the case of semiconductor materials, the valence band, conduction band, and valence band, it's partially filled with conduction band, and some cases is too much overlap. So that's why when you make the design of the solar cell, we need to confirm about the band gap value, whether it is some high mismatch or less mismatch. So every times we consider the band gap should be adjusted with less mismatch value, then the ultimate device efficiency will be improved. So actually a solar cell is just kind of some PN junction material. So I just want to show some forward and reverse bias. Actually this is some very basic fundamentals of our semiconductor materials. So this is some P and N type material. So when the P type material is some equilibrium, then the Fermi level is very close to the valence band, and for the N type case, the Fermi level is up to the valence band and it's near to the conduction band. And if we make some applied voltage, then there is some diffusion and deep current produced in the PN junction, then the current and hole are follow, and then ultimately the device is some complete. So this is very fundamentals of some semiconductor materials according to forward bias and reverse bias or biasing condition. And in also solar cell, various types of solar cells, some of them is some direct band gap materials they are using, and some of them is some indirect band gap materials is using in the fabrication of solar cell. So direct band gap means if the maximum of the valence bands and uh, conduction band minimum is not in the same on the Brillouin zone, then that type of band is called indirect band gap materials. But if the bottom of the conduction band and maximum of the valence band is aligned in the same Brillouin zone, then it is called direct band gap materials. So both direct and indirect band gap materials are being used for the fabrication of solar cell. So now let's move to the some uh, division of the solar cell. So here there are several types of solar cell, but here I want to focus only some silicon solar cell and non-silicon solar cell. So usually silicon solar cell is divided in two types of material. One is single crystalline silicon solar cell, and another one is polycrystal silicon solar cell. So both are silicon solar cell, but one is single crystalline and another one is polycrystalline, and their the appearance difference. So because of their grain size is different. For the silicon solar cell, there are two types of solar cell. One is single crystalline solar cell and another one is polycrystalline solar cell. Both solar cell is silicon based, but their main difference is one is single crystalline and another one is polycrystalline. So polycrystalline means there is more than one, at least more than one grain structure. But for the single crystalline silicon solar cell, it's some only on crystal formation. And actually for the now for the business or industry purpose, single crystalline solar cell is almost 90% used rather than polycrystalline silicon solar cell, because crystal silicon solar cell has high device performance. So another solar cell is some non-silicon based solar cell. So non-silicon based solar cell is divided mainly two parts. One is organic and another one is inorganic. So if we compare some organic solar cell, then dye synthesized solar cell, polymer solar cell, and for inorganic solar cell, there are CIGS solar cell and cadmium telluride solar cell. And another one now is very promising solar cell is perovskite solar cell. It's some organic inorganic based solar cell, but due to their stability issue in the air, it's not applicable for the industry purpose. So my research is just focus on CIGS solar cell. It's very stable in the ambient air condition. It's also stable some humidity and some temperature consideration. So that's why my research topics today covers these types of CIGS solar cells. And also there are several special types of solar cell. This is for flexible solar cell and some transparent solar cell. So both of them are using some for commercial purpose. So flexible solar cell is used some electric car and apartment like others in the some multi-purpose case. And application of solar cell is some building integrated PV. That means we can cover the building by solar cell, then it can generate the electricity by automatically. And some smart farms, some electric vehicle, and also some special space photovoltaic, all of them are using some flexible or like some solar cell. So this is the famous chart of solar cell based research cell efficiencies. So it's some NREL, National Research Energy Laboratory of USA. So if we just focus on the green, so now the highest device efficiency is around 23.3% of CIGS based solar cell. So now I am just going to focus the schematic of the chalcopyrite solar cell. So usually CIGS solar cell is consisting, or CZTS is consisting of different types of layer. First, bottom layer is some moly-coated glass, then some CIGS absorber layer. Then we fabricate some cadmium sulfide, that is some buffer layer, we call in the solar cell term it's called buffer layer, and then top is some window layer. So here is two part. From glass to CIGS, it's some p-type layer, and up to from cadmium sulfide to zinc oxide, it's some n-type layer. So ultimately solar cell is the combination of p and n-type layer. And if we see the energy diagram or band diagram of the total device structure, then we can see that usually the CIGS band gap is 1.2 electron volt, and this cadmium sulfide, this is n-type layer, its band gap is 2.4 electron volt. And this the window layer, this is the top layer, its band gap is around 3.3 electron volt. So actually when we fabricate some solar cell or some device, we need to very much concern about this buffer layer band gap, because if it's some too much spike or clip type buffer, then electron cannot easily pass through from the bottom layer to top layer. And if electron cannot follow easily, then the device efficiency is not too much good. So usually in the cadmium sulfide, there are two types of band alignment. One is clip type band alignment, and another one is spike type band alignment. So usually this is some clip type band alignment of the device. So actually this slide contains how we can approach to fabricate the solar cell in our device. So I just explain very quickly. So this is the spero deposition. In this spero deposition chamber, we just fabricate this absorber layer. Then we are using our absorber some high temperature selenization furnace to make this more crystalline. Then we approach some buffer layer, that means some n-type layer, and ultimately we can fabricate our solar cell in the twins RFDC magnetron sputtering chamber. And sometimes we are using some thermal evaporator with sputtering end. And others are the basic characterization tools that are used in my lab. There is some low temperature cryostat, solar probe station, Raman, lock-in thermography, and potentiostat, AFM, and some atomic layer deposition, and some TRPL that we are using for our device characterization in our lab. Okay, so now I am going to my main part. Now I am going to discuss this research paper that we have published in 2019 in ACS AMI. So actually that paper contains some sulfur-alloying effects on CIGS solar cell fabricated by using Aqueous pyrolysis system. Okay, so this is the same image of the absorber. So if we see, actually this research paper were published on the basic of how sulfur alloying effect in affects the device performance. So actually in the CIGS solar cell, C means copper, indium, gallium, sulfur and selenium. So in this case we alloy sulfur with respect to selenium, and then we just analyze how sulfur alloying can impact the device performance. So when we check the absorber after preparing the absorber, then we see that with this is without sulfur, and with increasing sulfur we saw that the grain size is little bit increase, and after that it's some for high sulfur concentration the grain size is too much decrease. But and also with increasing the sulfur content we saw that the surface was a little bit smooth. So this is the analysis from this image. So it's indicated there's more sulfur alloying such as sulfur 0.3 with respect to selenium, the surface roughness is decreased. And usually for the low rough surface or smooth surface is desirable for the fabrication of solar cell, because if the surface is too much rough or surface smoothness is less, then the junction formation of our device is not good. So usually when we make our device, we need to uh, confirm that the surface is smooth. Okay, then we analyzed our film with some XRD data analysis. So here is we see that with increasing the sulfur content, the peak position is little bit shift. So peak position shift to higher angles means it's implying that the decrease in the lattice constant. So if the 2 theta angle is increased to the higher angle, that means the lattice constant of the absorber or our device or the film is lattice constant is decreased. And this figure 2c shows that a decrease of lattice parameter A and C with sulfur alloying. That means when you increase the sulfur with respect to selenium, then the lattice parameter is decreased, because we know sulfur is little bit less with comparing selenium. So when we add more sulfur with respect to selenium, then the sulfur site can be occupied by the selenium atom, because selenium is larger and sulfur is less. So selenium can be easily occupied by the sulfur. That's why with increasing the sulfur, the lattice constant or lattice parameter is decreased. And when we plot the full width at half maxima, it is observed that the sulfur alloying case, the full width at half maxima is increased. So full width of half maxima is uh, uh, increased. That means the crystalline grain size is decreased. So if we just figure out this Shear's formula, that means crystalline size is totally reverse of the full width half maxima. Here lambda is the XRD wavelength, so copper K alpha wavelength 1.54 angstrom, and W identify the full width half maxima, cos theta is Bragg's angle. So we see that the crystalline size is reverse of the full width at half maxima. That means with increasing sulfur, the crystalline grain size is decreased. That we also saw in the previous slide with same image. With high sulfur content, the grain size is too much decrease. And we also calculated the crystalline grain size from without sulfur to high sulfur case. We saw that with increasing sulfur, the crystalline size is reduced from 24 nanometer to 13 nanometer. And if we further check the Raman analysis of our absorber, we also see that for the case of CIGS solar cell, there are two types of phonon vibration mode in the Raman analysis. One is selenium vibration mode, and another one is sulfur selenium vibration mode. And we see that this is the main peak of the Raman, and it is denoted the A1 peak. So this A1 peak is 174. And if we see the peak position of the A1 mode, we see that the peak position is shifted to higher frequency. That means higher frequency means it's some blue shift. And also there is some selenium sulfur vibration, and it's about some 294, and this vibration is too small, because for the our device or absorber quality, the dominant phonon vibration mode is selenium vibration mode, and it exists around 174. So we can conclude that with sulfur alloying, the selenium vibration shifts to higher frequency, and for sulfur phonon vibration modes, it's slightly to the lower frequency. And we also figure out the from the figure D, this figure is respected the total integrated area of this peak intensity. So this also supports that the sulfur alloying increases the area of the total integrated area. That means sulfur is well substituted into the selenium site, and resulting the formation of the CIGSSe. So here in this figure up to sulfur 0.3, we observed that there is some sharp peak, but in the case of sulfur 0.4, we saw that the peak is not so much sharp. That means there is not single peak, it's some secondary phase is appeared. Then we further analysis the secondary phase, which types of phases are present in this spectrum. So if we further check that spectrum only, we see that in this spectrum also there is some copper indium gallium selenium phase at 159, 189, 200 on 218, and 295. So that means it's combination of too many secondary phases. So if it's combination of too many secondary phases, that means the crystal quality is not good. So that's why and also for the XRD we see that there is not single peak, there is some several secondary phases peak. So we confirm that this secondary phases peak also arises from the some secondary phase of the CIGS, or copper indium selenium or copper indium gallium selenium phases. So this is the some reference PDF card for XRD confirmation that we have studied to further confirmation where is the peak is come from. So that means that high sulfur is not beneficiary for the device, and high sulfur contained device shows some multiple secondary phases, not unique phases. But our main concern to phase the only single crystalline phases, that means it exhibits only one sharp dominant peak, not too many other secondary phases. And okay, so now uh, before up to that slide, there is some characterization of our device absorber, and now we are going to fabricated our device, and now we are just analyzes our device. So here we see that the VOC is increases, that means open circuit voltage is increases up to 0.3, then the pink is 0.4, it's decreases. So the increment of VOC is due to the passivation of some recombination center and the space charge region. And we also believe that there is some better band alignment between the absorber and buffer, and upshift of the band maximum to the CIGS observer, which resulted from the S-alloying. So in the previous slide, I also just mentioned that for the solar cell device formation, this band gap is too much important. So if it is too much spike or too much cliff type, then electron cannot pass through. So so in our experiment, we believe that with some optimum sulfur alloying, the better band alignment is improved. And the VOC deficit of sulfur alloying is also decreases, and VOC deficit is also related some electrostatic flux, charge fluctuation, and some band gap fluctuation. So this is the basic device fundamental characteristics that we observe from the optimum sulfur alloying case. And as we more sulfur is alloyed, if we put more sulfur, then the grain size is decreased, and if the grain size is decreased, then it accompanies by some portion of the grain boundary region, that means it too much segregated. So if it is too much segregated, then there is too much electron loss in the segregation, and also some it acts some defects. So if it acts some defects of some trap levels, then the electron cannot move through from the conduction band to valence band. So if it produces more grain boundary, so that grain boundary creates some defect level, so that defect level is decrease the band alignment. And that's why we see that for the case sulfur 0.4 case, the device band alignment is little bit decomposed of some defect levels. And for the external quantum efficiency graph, we also see that up to below 700 the EQE curve is decreased, but all other cases were improved up to 500 to 900 nanometer range. That means the sulfur 0.4 that contains high sulfur and too much grain boundary, and it creates too much trough. That's why the wavelength is drop. So it's our conclusion from the device parameters. We just concluded that high sulfur is not desirable, but sulfur is desirable up to optimum level. So this is the device performance table. So we see that with increasing sulfur, the device efficiency is increased. So sulfur 0.3, we got the 10.89% efficiency, but with more sulfur, then the efficiency sharply drop, and also the JSC is drop, fill factor, and some VOC others parameter is too much drop, because with more sulfur it creates more defect or some trap level. And now we are further characteristics our device with some photoluminescence and time resolved photoluminescence analysis. So usually for the time resolve or some photoluminescence strategy, we usually expect some high intensity spectrum in the wavelength range. So if some device shows some high intensity spectrum, that means the device absorber and buffer layer quality is good. So here in the PL spectrum, we see that the green line is contains some green line and blue line and red line all are comparing good spectrum with comparing uh, sulfur 4. So here also sulfur 4 some low intensity spectrum, that means sulfur 4 is not good. And we also analyze the uh, time resolved photoluminescence for a device minority carrier lifetime. Here you also show that for increasing sulfur the lifetime is increased and up to 0.3, and when it reaches 0.4 the lifetime is sharply decreased. That means for the PL case we observed that a higher band gap is shifting with more sulfur alloying. And in the PL there are several types of transition. One is from band to band transition, do not to acceptor transition, and trap level to band transition. So there are several transition occurs between the conduction band and valence band. So the longer lifetime indicates the reduced recombination defect level in the absorber. So in the when we measure the PL, there are two types of recombination. One is radiative recombination, another one is non-radiative recombination. So radiative recombination is usually we desire for the good device fabrication. So the device or some solar cell which has radiative recombination, that device shows some high spectrum, and the device that contains some defect level, that radiation is non-radiative recombination. That non-radiative recombination is some band to trap or trap to band transition, it's not from band to band transition. And we also analyze some JVT analysis. So actually this is very special analysis for the characteristics of solar cell. So in the JVT analysis we conduct this experiment from room temperature to 90 Kelvin temperature using some low temperature cryostat chamber. And we see that for the sulfur 00 case, that means without sulfur case device, we said we can observe that for the low temperature case, this actually this y-axis is current density, the current density is sharply decreased. But for the sulfur 0.3 case, we observed that the current density is not decreased. So the JSC decrease at low temperature is due to the depth level and its defect density. That means when the temperature is lowering, then JSC is sharply decreased. That means there is some deep defect level or defect density in the device. And also we also it also relates that some trap assisted recombination rate with charge emission rate is temperature is lowered. That means when the charge emission temperature is lowering, then the recombination rate is increased. That means electron slowly move up, move down, then it can easily occupy in the intermediate of the between two state, valence band and conduction band. The increase of charge recombination rate induces a decrease of photocurrent because electron cannot pass through from the conduction band to valence band, and it also easily occupied. That means if it cannot go directly from the conduction band to valence band, ultimately the photocurrent of the device is decreased. And here we also some calculated some activation energy of our device. So we see that for the sulfur 0 case and sulfur 0.3 case, this activation energy both is for sulfur 0.3 case, the activation energy is higher. So if the band gap and activation energy, that means EG and EA is larger. EG means band gap of the device and EA means activation. So if the difference is larger, that means interface recombination is stronger. So which so if the interface recombination is stronger, then the JSC, that means short circuit current density and open circuit voltage, both are reduced because it cannot go pass through the up to conduction band or to valence band. So ultimately if this happens, then the device efficiency is decreased too much. So actually this table I am just planning to show you why we approach this method. So you see that this is some highest efficiency is yet obtained. So in our lab we usually use some pyrolysis. So in the pyrolysis case, it's the highest efficiency is 17.3, but they use some hydrogen based solution. We know hydrogen is toxic, so usually we just want to avoid these types of toxic solution. And also there is some metal nitrate solution in mixture of 2-propanol and ethylene glycol. So ethylene glycol has some toxic, but others pyrolysis method among some non-toxic solution base, our result shows the highest among the solution based pyrolysis method. So this is the supporting information of the reference, this reference table. And so ultimately I am just conclude my talk. So first we fabricated some CIGS solar cell using aqueous pyrolysis and subsequent post-sulfo-selenization. That means we use some sulfur and selenization. And for sulfur-alloying case, we found the optimum sulfur content highest efficiency. And also for the optimum sulfur alloy case, it enhanced the open circuit voltage and it's increased the band gap and with some passivation of the defect level. And for the JVT measurement showed some negligible surface recombination for the sulfur 0.3 CIGS solar cell. So that means for the JVT measurement, it shows that the recombination is less, but without sulfur, the recombination was high. Okay, so this is the author information. So this work is conducted by our group leader, Professor Juno Kim. So he was the corresponding author, and this work is supported by the National Research Foundation of Korea and Korea Institute of Energy Technology Evaluation Planning and Ministry of Trade and Industry and Energy of the Republic of Korea. And I used some reference of this total presentation. So here I just mentioned some of the reference that are included in the reference. And here is our group, our NPDL. So actually in our group, we are not too much many people. We are just doing some 4 people with our professor. Okay. Okay, thanks to all.
Thank you, sir, for your nice presentation. Please, if anyone has any question, please ask.
I had a question I
Okay.
wanted to ask. Okay, so my question was, you were discussing about the lattice parameter. I would like
Yes.
to know that how the lattice parameter would affect the efficiency of our solar cell.
Okay. So actually, before going to discuss with some lattice parameter aspects, so first we need to observe some field emission scanning electron microscopy image. So actually, we use this approach to observe the surface of our absorber or our film. So if our film surface is too much rough, then we cannot use that absorber for the fabrication of solar cell, because if it's too much rough, then the mismatch between the absorber and buffer layer, that usually we call some buffer layer, it's not well matched. So if it's not well matched, then there is some trap level also created here. So actually that surface smoothness is requires to the absorber and buffer layer. Okay, so we are usually observe some good device is formed when the absorber surface is smoothness is good, surface is smooth. So if we see that for the high sulfur case, we see that this grain size is too much small. So if grain size is too much small means very small grain, many grain boundary, right? Do you hear me?
Yes, sir, I can hear you.
Okay, so if many grain, small grain, that means many grain boundary. So many grain boundary means many electron pass trap level or electron can pass that grain boundary region. And if electron can pass that grain boundary region, that means electron can be trapped between the valence band and conduction band. It cannot reach to the valence band. That's why there is some defect level. So that means if the lattice parameter is too much, here I explain, if the lattice parameter is peak position increase means lattice parameter is lattice constant is decreased. So if it's some higher angle for XRD, higher angle means there is some alloying effect is occurred. So if I just alloy sulfur with selenium, so sulfur is large and selenium is larger. Sulfur is small and selenium is large. So sulfur can easily occupy the selenium site. That means it decrease the lattice constant of the selenium with respect to sulfur. Okay.
Okay, sir. So if the lattice constant decreases, then it's beneficial to the solar cell.
Yeah, actually it's beneficial up to certain optimum condition. So if lattice constant is too much decrease, then it's also not good. Or if lattice constant is too much increase, that's also not good. That's why we use some optimum sulfur. We can increase the sulfur more and more, but in our result we just in the XRD we see that up to 0.4 uh, there is some not single peak, there is some several secondary phases is occurred, but usually we cannot desire some secondary phases for the good device fabrication. We use just only sharp dominant peak. And also if we analyze the high sulfur in the Raman, we see that there is not single Raman phase. There are so many Raman phases appeared on the spectrum. So that is not beneficiary for the device. That means the crystalline formation of that observer was not good. So if the crystalline formation of that observer is not good, we cannot expect the good device efficiency by using such kind of observer.
Okay, sir. Thank you.
Okay.
One question is asked in the chat section. Is CIGS direct or indirect band gap material? Out of the direct or indirect band gap material, which are better for solar cell fabrication?
Okay. There are so many contradictory results or contradictory research about whether CIGS is direct or indirect. So actually that's the not main issue. Our main issue is the optimize some band gap structure. So several research group claim that they found that the transition is little bit some indirect types. Several groups reported its direct type. So actually this is some controversially result output. But in our case, we believe that this is some direct band gap materials. In the band gap aspect, there is many controversial, but usually we believe that it is some direct band gap materials
Okay,
because
yeah,
uh,
thank you.
because in our schematic structure we didn't show any types of intermediate layer between the absorber and buffer, so it's just sandwich. So we considered that electron can easily pass through from the absorber to buffer without any intermediate transition. So that's why we consider it's some direct band gap materials.
Another question is posed in the chat section by Mohammad Ghulam Hafiz.
Okay.
What is the environmental effect of CIGS solar cell?
Actually, CIGS is basically there is non-toxic element and all elements are earth abundant materials, so it is not so much costly. But one thing is considering issue. Usually in uh, our CIGS fabrication that we proposed in our experimental talk, we use some cadmium sulfide buffer layer. So actually we know cadmium is toxic, but many other buffer layer is also proposed. Buffer layer actually for n type layer. So this buffer layer is some combination between the window layer and absorber layer. So buffer is some intermediate layer. So now the researcher wants to move some cadmium free buffer layer because cadmium is toxic. So if we consider some cadmium free buffer layer CIGS, then there is no concerning some environmental issue if we remove the cadmium sulfide buffer layer. So there are many buffer layers such as indium sulfide buffer, some zinc tin oxide buffer, some zinc oxide buffer. There are several types of buffer layer. So that's types of buffer layer now are replacing the cadmium sulfide because cadmium is toxic and it has some hard bad impact to the environment. So if you consider without cadmium buffer CIGS, then it's not a problem to the environment. And it's also now CIGS solar cell is also some commercial production in Korea. So in industry they fabricate, they produce solar cell for the commercial purpose, CIGS solar cell.
So thank you for your excellent presentation. Actually, I wanted to ask a question. I actually want to make the connection between our undergrad study and your research. I want to make that point here. I want to make mention that point. Actually, the last semester, I taught them about the monoatomic lattice or diametric lattice and the vibration and the mood of them. So actually, whenever the lattice constant decrease, then the K, I mean the number of wave number will increase. That means the efficiency increase to absorb a large number, a large band of the it increase the absorb of a large band that increase the solar cell efficiency. But there have some another problem is arise, like whenever you decrease the lattice constant, then there are the more they make more segregation that make a large number of trap of the electron flow. That's why in another way it decrease the efficiency. So we need a optimum. We need to optimize here. We also decrease the lattice constant, but not too much, such that it doesn't make more segregation, because it hamper the electron flow. That is the point, right, Salahuddin?
Yes. So if yes, your assumption is correct. So if the grain size is too much small, that means there is so much grain boundary. So there is so much grain boundary means it's at some trap level. So there are so many electron can passes many paths from valence band to conduction band. So if electron get chance to many path to from conduction band to valence band, so ultimately it trapped many some shallow defect, some deep defect. There is some so types of defect is produced if the segregation
that's why we cannot reduce the lattice constant
too much less,
too much, but we need to keep
optimum.
in optimum value. So such that the both purpose will serve for us.
Yes.
This is the point, and your presentation is very clear. I understand it, and my physics is very good to explain. My physics is very good to explain.
Actually, I thought that maybe it will be hard because every research system is specialized. So I just tried to more generalize to focus how I can explain more easily.
Yes. No, it is the point. When you understand the very simple physics, but you already we already know that physics have been used here to explain the things here. I think it is very, very clear to me, and I think the students, those who are attend this seminar, we should remember that we no need to learn many things. Here you find very simple thing. Actually he sharpened the point, which point we need to focus, and he did lots of experimental work. Then he find that result. Now he tried to understand it by the very good physics.
Thank you very much, sir, for your nice presentation.
Okay, actually I know it was not nice.
I have two queries. One is, what is the efficiency of your present solar cell? And if it is direct band, have you calculated the band gap calculation theoretically, or you have any plan to calculate it? Or my another query is, what is your next plan to increase the efficiency of this solar cell?
Okay, so
thank you.
Okay. Actually, in our lab, we are using some pyrolysis system, and to the best of my knowledge, we are the single group in the world. Others group are trying some highly vacuum based fabrication solar cell, but in our lab our result is some it's close to the world champion device, and we are preparing some manuscript. So Rinku, it is still under some process, so I cannot explain here what's the efficiency, but our efficiency is very close to the world class efficiency. And another one is usually we didn't do some theoretical work. We can just estimate the band gap of our device from the EQE extraction and also PL measurement. So we don't do some theoretical work. We just calculate our band gap from this, and also from this peak to here. by this way we can extract our band gap. We don't do some theoretical work. And our efficiency is already I mentioned, it's somewhat very close to the world class, but it is under processing for publication, so I cannot disclose here. And actually we are trying some easy way that we can more generate for industrial purpose. In Korea, every research is correlated with some industrial purpose. So already some of the industry are using our approach, our method, and we have some patent from our lab. So we already applied for patent to the Korean government for our device fabrication approach, and our result is world class. Just I can mention is like this, because still we didn't publish our result yet, so I cannot explain what's the highest efficiency, but efficiency is close to some world class efficiency.
Thank you, sir. Thank you for your answer. Another thing I want to mention that you have told that your solar cell is a direct band gap semiconductor solar cell.
Yes, yes.
So direct band gap semiconductor has several advantages over the indirect band gap semiconductor, which we conventionally used in silicon or germanium solar cell. So if the efficiency level is very close to that, then it will be a nice invention from your group, and advanced congratulations for that.
Yeah, actually, Rinku, now this if we consider some CIGS solar cell, the world efficiency is around 23.5, 23.55. But actually they use some highly vacuum process for the fabrication, and highly vacuum costs too much money. But in our lab, we just produce a solar cell in normal air without any vacuum. So that is our main strong point in our lab, because in the world other labs are trying some vacuum base, and they're trying more and more to improve the efficiency. But in our case, we are using some ambient air condition, no special vacuum, no special care, and it's also stable in humidity, not affected by temperature. So it's more stable in our fabrication approach. So that is the more strong point for our result when we submit to some paper or others. So we just focus, we are using some normal condition, and we also use some solution, and here the solution is also not so much expensive, and we can use the solution on solution several times, so that is not too much costly also.
Thank you for your explanation.
Okay, so I have two questions. Okay, if I'm saying that this correctly, you talked about Brillouin zone. Can you provide the definition what is the Brillouin zone is? And another question is, you talked about organic solar cell. So is it some drawback that when we use organic solar cell, because it is organic, does it get affected by the outer world or nature faster than inorganic solar cell?
Okay. So first, Brillouin zone actually some if we consider some lattice or basis. So Brillouin zone k equal to 0 means that is we consider the center. So Brillouin zone 1 k equal to 1 means there is some spherical or some other shape. So I think Brillouin zone is some hypothetical zone that we can use for identify some lattice or some basis like this, as I remember, but I need to more clear, because actually in our research case we just mentioned some direct and indirect materials, and I just focus k equal to 0, that means it's on the center of the Brillouin zone, but I didn't explain more, so maybe for further explanation I also need to check. And second question is, organic solar cell is not so much stable in in humidity or air, because in organic solar cell, this organic compound, there is hydrophilic or hydrophobic compound they are using. So hydrophilic or hydrophobic both are affected by the humidity, and usually solar cell is installed in the air. So if it's affected by the humidity, so then maybe ultimately 5 years or 10 years the efficiency is decreased. But when we think it's some commercial purpose, So we need to stability, air stability. That's why we are considering some inorganic solar cell. And if you consider some high efficiency, perovskite solar cell is the world highest efficiency solar cell. But one problem is it's degraded too much quickly in the air, because in the perovskite solar cell there is some hydrophilic or hydrophobic layer that is also affected by the humidity. So that is the main concern of this perovskite solar cell. So if the humidity or stability issue can be solved the perovskite solar cell, then perovskite solar cell can be the world leading renewable energy resources with comparing other source, because almost perovskite solar cell it crosses the 30% efficiency, but limitation is it is not stable in air and it's affected by the humidity. In inorganic solar cell for cadmium telluride, or if you consider some CIGS solar cell, actually this is inorganic and we usually some chemical salt and mixed with some DI water. So it's not affected because it's already the solution is mixed with DI water. It's already adjusted with air molecule, water molecule. Some hydrogen, oxygen is already accumulated. That's why it's not too much affected with humidity or in the air. That's why we are using inorganic solar cell.
Sir, thank you.